change the delta function into an integral, you divide by 2 pi dt. Okay. T over 2 minus t over 2. And then somewhere I need to say that this is the limit as t goes to infinity. Okay. And that is e to the I omega m prime minus m plus omega. Okay. Now, since this integral is multiplying the delta function, I know that the delta function only takes value is everywhere 0 except when these are equal. Okay. So it makes sense to set whatever is in the integral equal to that because it's scaled by this thing. Okay. When I set this equal to 0, the integral becomes 1, right? And then the integral is just integral over 1. Okay. And it comes out to be t over 2 pi. Right? So that the probability of the I to m's transition is equal to, in the limit, in the steady state limit, okay, 4 pi squared and 2 pi cancel. Oh, sorry, I forgot the h bar squared. So this is just 2 pi h bar squared. Okay, and then you have this matrix element. And then the delta function doesn't change. Okay, and then over here is just t over 2 pi. Okay, so it's a linearly growing thing, which is bad. But if we were to make sense of it, we would study the rate of change. The rate of change as I go to steady state. So the rate of change is the probability divided by the time for the experiment. So the rate of change then is a very nice formula. And this is called the Fermi's golden rule. Yeah. The rate of change for this R for the I to m's transition and the steady state limit is given by, okay, 2 pi over h bar. Let me write just h bar now. Okay. Phi n h p naught. 5I squared, okay, and then we're going to get a delta function. Oh, sorry, there's no 2 pi. I divided by the 2 pi from the 4 pi squared, so this is just. And then when I divide by t, the t disappears. So I'm just left with the delta function divided by h bar. Okay. So it's delta omega m minus omega I plus omega divided by h bar. Now, delta a x is equal to delta x divided by the magnitude of a. Okay, everybody should know this formula. So now I can go ahead and multiply h bar inside of the function, right? The delta function. So in the end, I get Fermi's golden rule. And the Fermi's golden rule is really easy to remember. Okay. 2 pi over h bar, just remember this factor. One of the 2 pi's comes from one of the, because we had 2 delta functions and we got rid of one by going to the rate. Okay. So one of the 2 pi is left over from there. Okay. One of the h bars went into here, but the amplitude was minus I over h bar coming from the Schrodinger equation. So one of the h bars is left here. Matrix element squared, of course. Okay. Delta function means energy conservation of energy in the steady state limit. Okay. All right. So this is Fermi's golden rule, and this is the simple version of it for sinusoidal perturbation. And later we're going to study. Maybe if we have time, we can study the full version of it for arbitrary f of t. And that is called the interaction picture.
When you mentioned that R is just equal to P over T.
Okay, so
if you find your R.
I over divided by the limit. Okay. Any questions? So in the steady state case, okay, if I observe long enough, energy is conserved. But as you saw earlier, okay, if for a really, really short time, because neither the experimenter or the system knows the real frequency of the perturbation, so there's no sense of energy conservation because they don't know the frequency. All right. So are there any questions? Yeah, we don't have time to go into more formalism stuff, but really I just wanted to show you that there is such a thing called the time evolution operator, which is given by e to the minus to exponentiate the Hamiltonian. Okay, and by putting the time evolution onto the state or the operator, you can have two different kinds of quantum mechanics. But maybe in the future when we really need this, we can talk about it. So to the next lecture, we're going to start chapter 7. Okay. Yeah. If there are no questions, you can pick up your homework and your results.
You give a very simple lesson time on Thursday. Okay. According to the schedule, you're supposed to actually come on Thursday.
Yeah, you have learned quite a bit now, right? So after learning perturbation theory, there is some exam problems that you can test.